Conservation of momentum. In the last section, we learned that momentum can only be changed by an impulse from a net outside or external force. So let's imagine two skaters standing near each other. They each have zero momentum. They're not moving. So since momentum is mv, there's zero momentum. When they push each other away, we know they both gain momentum. They both have a velocity now. Okay, one's in this direction, and this is the key. The other is in this direction. But there is no outside force, right? The force between these two skaters, we consider them as one whole system. It's an internal system. They're pushing on each other. So where did their momentum come from? And that's the question up here. Where did their momentum come from? Where does it go? Outside force was defined as a force that acts on whatever object we're studying. And in this case, the object we're studying is the pair of skaters. So we're expanding the definition to an outside force is a force that acts on whatever objects we're studying. And another name for that, which you'll see in probably your next physics course, is a system. We have a system of objects. So let's study these two skaters. So the forces they exert on each other are not outside or external forces. They are inside or internal forces. Now let's get back to our skaters, or our thought experiment, or our Gedanken experiment. That's German for thought. The two skaters standing near each other started with no total momentum, zero momentum, just like our carts. They had no velocity. What is the total momentum of the skaters after they push each other? Consider, are there any outside forces acting on the skaters? Well, no. And if this works, just like our experiment did, the total momentum after they push each other is also zero. There are no outside forces acting on the two skaters, so the total momentum of the two skaters doesn't change. And hopefully you found that out in the lab you did with the carts. Started with zero, ended with zero. So the final momentum of the two skaters is zero. But each one has a momentum because they're moving. Where does that come from? When they push each other away, we know from Newton's third law that they push with equal and opposite forces. These will be inside forces to our system of the two objects, the two skaters. The force that blue exerts is negative of the force that orange exerts. They also push each other for the same amount of time. So T sub blue equals T sub orange. Let's put these two pieces of data together where we have the forces and the times. And since they're equal and opposite and the times are the same, we can say that F blue times T blue is equal to negative F orange times T orange. Okay, because these guys are the same. So I basically multiply F blue by T blue and F orange by T orange. Impulse is delta P. So our impulse, probably should have written that there, force delta T is impulse. That gives you a change in momentum. So the change in momentum of blue is equal to negative the change in momentum of orange. Right, here's the blue guy, here's the orange person. The momentum that the person in the blue coat gets is the negative of the momentum of the person in the orange coat. They each have a momentum from the force exerted by the other person, but the total momentum of the two people here, the two objects in our system, does not change. All right, two reasons for that. One, there are no outside forces, and the other reason is this right here. You add up the two changes in momentum and you get zero because it's a vector. There are only the inside forces of the skaters pushing on each other, and that does not change the overall momentum, the net momentum, the total momentum of the system of two skaters. We can now talk about the law of the conservation of momentum. As demonstrated by our little thought experiment, and also hopefully the card experiment worked for you, momentum is conserved, which means it remains the same, it does not change, during an interaction, as long as the objects are not affected by outside forces. Say it in a different way. The total momentum of objects prior to hitting each other or separating from each other will equal the total momentum of the objects after the interaction, as long as there is no external or outside force. Any momentum lost by one object is gained by the other. Right? If you had a negative momentum and it's negative x, the other object would have to have a positive momentum, plus x. We say that momentum is conserved. This is a law of nature. It works all the time. A Newton's cradle, see that in a lot of physics labs, demonstrates conservation of momentum as the outside spheres take turns moving. And don't just be satisfied with moving one of the spheres out. You could also try 2, pull that out and see what happens. Then try 3. It's really cool. The next chapter will provide more detail on how conservation of momentum is used to analyze interactions between objects.